Okay, so the final talk of the session will be given by Alma on correlation.
Hello everyone, I'm very excited to be here. So thank you for joining my talk. This talk is going to be about sublinear algorithms for condition clustering. As Google motivated this morning, we are going to explore local searches and local changes in the pivot algorithm, which you may know that this is a very this is a combinatorial result that gets a constant approximation for correlation clustering. We are going to explore beyond that way. This is an upcoming joint work with my advisor Soheil, Moses, Vincent, and what is correlation clustering is that the general definition is that you're given a set of data points and the pairs are labeled as similar or similar, and some of them are not labeled. What we want to do is to, our goal is to cluster these data points in a way that the similar edges are clustered together and the similar ones are clustered apart. If we have the input as we have all of the graph, all of the pairs labeled, then we can actually model this by a graph. So in this talk, I'm going to use the definition of the graphs, which is we have a similar pair as an edge, and it's dissimilar pair as a non-edge. And then our goal will be to partition the vertices into clusters such that we minimize the number of disagreements in the graph. By disagreement, we mean when we cluster two endpoints of a non-edge, we get a disagreement. And when we partition two endpoint of an edge into different clusters, then we also get a disagreement. For example, here we have to pay for all the non-edges inside each cluster and for any edge between two clusters. So the total cost here is 4. And in this example, we have to pay a cost of 7 for any edge between any of these two clusters. So let's take a look at the prior work. Correlation clustering was introduced more than 20 years ago by Behnezhad, Bloom, and Chada. It was proven to be apex hard. After that, there has been an extensive work on the problem and the polynomial time algorithms. That the best one that I know of actually goes as little as 1.43 approximation. And some of these results, although may rely on happy solution, are actually implementable in sublinear models as well. There is another line of work using pivot algorithm, which was introduced in 2005 by Weiyun, Charikar, and Alma. And this is a combinatorial result that gets a 3 approximation. So there has been a lot of implementation of pivot algorithm on sublinear models that I'm going to talk about more in the rest of the talk. Okay, so let's just start about what is a pivot algorithm. So what we do is that imagine we have this graph as an input. We just pick a random vertex as the pivot. We then remove all these neighbors and put in a single cluster. And then we just do this again and again until we don't have any vertices that is not clustered in the graph. So here the output of the pivot would be something like this. The pivot algorithm, it guarantees a 3 approximation in expectation for correlation clustering. And this is actually a type result for the pivot algorithm. The pivot algorithm cannot do better than 3. And also, it also it's used a lot for rounding algorithms in happy solutions and efficiently implementable in sublinear models such as fully dynamic, MPC, and also semi-streaming. So these models, we can get actually almost 3 approximation for correlation clustering. So this actually brings the questions that can we get better than 3 approximation in any of these models? So to be able to answer these questions, we are motivated to find out what is the problem with the pivot algorithm, what is the cases that is hard to actually beat 3 in the pivot algorithm. So let's take a look at this example here. We have a complete graph that has an edge between these 2 complete graphs. And then what happens here is that if you want to get the optimal solution, we put each one of these complete graphs in one single cluster, and we pay cost of 1 for this edge between the 2 complete graphs. However, the pivot algorithm might sometimes pick one of the edges between these 2 complete graphs, and then we actually we will give a cost of n because we have to now pay for all the vertices, all the non-edges in the clusters, and also the edges between 2 clusters. So what happens here intuitively is that the pivot algorithm fails to somehow see that if 2 vertices they are connected, but they have very different neighborhoods. So it cannot actually distinguish between these 2 solutions. And also another problem could appear here, that we have a complete graph and that without an edge, a specific edge. And what happens here is that the optimal solution would be just to put this in one cluster. And so if we do this, we actually pay only a cost of 1, but with a probability of 2 over n, we might actually pick one of the vertices of this non-edge, and we actually might pay a cost of almost n. And this way, the expected cost would be actually 3, and this would be also a type example. So here also the problem is that the pivot algorithm again fails to see that if there's a non-edge between 2 vertices, and they have very similar neighborhoods, we have to cluster them together. So the pivot algorithm does not do that. Okay. So our contribution is that we actually provide an algorithm, modified pivot algorithm, which is implementable in many sublinear models, and also gets a better than 3 approximation for correlations. And the sublinear models are fully dynamic. We can get a better than 3 in fully dynamic MPC, and also semi-streaming. There is also a very interesting result. This is also combinatorial on the MPC model, but gets a very better approximation, 1-point approximation for the MPC model by Vincent. So let's see how we actually solve these problems that I mentioned before. So here we said the problem would be in this example that we pay the cost of n. What our solution would be is that we just put the vertex that has very different neighborhoods from our cluster to a single cluster. This way, we're not paying for the non-edges between 2 clusters, and we would be just paying for the edges, and the cost would drop, and we can beat the 3 approximation here. So the intuition would be to put this in a singleton cluster. And also in the second example, what we could do is that if we see a vertex that has very similar neighborhood to our cluster, then we just add it to the cluster. And this way we can again decrease the cost and put through. But here our intuition might actually go wrong. So let's take a look at this example. This is This is an unbalanced complete bipartite graph. And then what happens, the pivot might pick one of the vertices from the side that has too many vertices with higher probability. And then we would just cluster the vertices from the top part with this vertex. So our intuition from the problem 2 would say that we could just add all of these vertices to this cluster because they have very similar neighborhood to the first cluster. So we might add all of those, but this can actually go very wrong because we're adding the cost for all of these non-edges in the bottom part. So this doesn't seem to be a good solution. The answer to this is to just try to not add too many vertices or remove too many vertices. So what we could do is to just keep the size of the cluster with a constant fraction, at most with a constant fraction. So let it to just decrease or increase with a constant fraction. So we would just add at most constant fraction of the size of cluster to this cluster and also remove at most this much. So let me tell you about this modified pivot algorithm that we have. So for example, here, imagine that we have a we have run the pivot and we picked a pivot and it has some neighbors, and we put them in a cluster C. We have some vertices green outside of the cluster C that have very similar neighborhood to the cluster C, and we also have some red vertices that have very similar vertices to the outside of the cluster and very little similar vertices with the cluster C. So what we do here is that we just pick at random, at most a constant fraction of C from these green vertices, and also the same for the red vertices that we want to throw out of the cluster. So we pick constant fraction of the size of the cluster and add them, and the same for the removing. And we keep the size of the cluster small, that with the small changes, but we actually can say that this is just doing this is actually enough to beat the 3 approximation. This is our algorithm. This is
so you are assuming that you have some way of quickly figuring out whether the neighborhood is similar.
So since we are looking just at the cluster that we are inside, so I think we can do that for the future. So this is our modified pivot algorithm, and this just does some local changes to the pivot algorithm, and it's simple to go through. But there's some definitions about how we define the similar and dissimilar similarity between like 2 vertices that I'm not going to get into.
This actually modifies the cluster right after it's built, right?
So we actually prove that this is a post-processing step because we don't want to mess up with the pivot algorithm a lot. But
I mean, what you have here, it seems like it's like you build a cluster, you modify it, but then you can say that you can equivalently do this as post-processing, right?
So we have to be very careful about if there's some so we have to let vertices be picked as a pivot later on as well. So we have to be careful about what vertices we are to like maybe label them if we want to remove them, and then remember that we want to add them to another cluster. Okay. So let's see how the analysis would work. There is a framework that is very well known for the correlation clustering algorithm that uses back triangles for this state. What a back triangle is that if we have a triple and it has exactly 2 edges, then we have a back triangle. The special thing about the bad triangle is that however we cluster a bad triangle, we end up getting a cost of 1 for this bad triangle. So if we actually identify k as disjoint bad triangles in the graph, then the optimal cost would be more than k, and this would also hold for the fractional packing of the bad triangles. For example, how the pivot algorithm would charge its cost would be that in this example here, we have to pay for the non-edges in the cluster. So we charge this bad triangle for the non-edges, and we have to charge for the edges that are between the cluster and the rest of the vertices. That we also have to pick a bad triangle to charge for this instead. And then how the pivot algorithm works and how the analysis of the pivot algorithm works is that we need to prove that the expected number of bad triangles containing any pair is less than 3. And if we can show that, then there is a primal dual analysis that this is a very elegant primal dual that says that the expected cost of the algorithm would be less than 3. So in order to apply this to our modified pivot algorithm, we need to make this expected result a little bit better to beat 3 in this, and then we can so we need to actually show that the expected number of bad triangles containing any pair is less than 3. So I'm going to talk about an example that the analysis could be a bit complicated in our in the analysis of the modified pivot algorithm. So imagine that the complete bipartite graph has root and vertices on the top and n vertices on the bottom, and then we could charge all of the triangles that we already charged from the pivot algorithm. But if we do this, there is some examples. For example, this one that we are at most adding a sub-constant number of vertices to this cluster. And then what happens is that we're not reducing the cost that we associated with each pair. So we have to add more bad triangles to our analysis, and we charge them as well instead of this triangle, or somehow fractionally with these triangles to distribute the charge over other edges, edge or non-edges, rather than the edge or non-edges that are like one endpoint of those are the pivot algorithm, the pivot itself. So here, for example, we would be putting a lot of charge on the non-edges between the pivot and the vertices from the bottom up. So how our analysis worked is that unlike the pivot algorithm, we would actually charge some non-local bad triangles instead of local triangles. And also, so what the pivot algorithm did was that it would just charge any mistake with a bad triangle. But what we are going to do here is to charge a set of mistakes with a set of bad triangles and do this fractionally actually. And to just conclude the analysis, we just need to prove that the fractional charges that we have add up to be more than the cost of the clustering that the modified pivot outputs. So let me talk about the open problems. So one open problem could be that can we actually do the analysis of the modified pivot algorithm better and get better than our result? And the open problem that still remains open is that can we get better approximation for any of the sublinear models, and also what is the best time we can use these models. That's it. I'm happy to answer any question.
So I have two questions. So what is the actual approximation ratio that you get? And can you get the same in the sublinear models with the current analysis?
Yeah, so the result is something like 3.9.
In 2.9,
2.9, yes, yeah, 2.99, and then, yeah, we can do exactly the same for the Socrates ones.
So like when you say better approximation for sublinear models, is it's the assumption that they may be in some sense stronger and that would allow for lower approximation or?
No, so I mean that the main question that we wanted to answer was for sublinear and so.
So maybe I'm not confused. I thought you said there was a 1.8 also in this something.
Yeah, there is
Is that a better, so doesn't that answer your second question?
That's just for MPC.
for MPC, yes.
Yeah, like for streaming or as for dynamic, like this from dynamic.
Doesn't even a modified algorithm provides an approximation factor for the problem of collision clustering with the objective of maximizing agreements on necessary. I'm not sure about that, but it's like. But if you want to like get a better result for the maximizing, then you have so the same result that works for minimizing works for maximizing the aggregates. But I'm not sure about it.
Maximizing agreements is much easier in building. That's the problem.
Oh, so it's option. Yes, the optimization is exactly the same. We have some solutions, maximizing the. Because already, yeah, that's.
Okay, no other questions, then let's head out to lunch. In fact, Alma, I guess.